What light in yonder window breaks and Juliet is the sun?
Who's the father?
No.
So she's a bright ball of gas?
No.
So someone's son is Juliet, is the star in the sky.
Hello world, welcome to Serology. In this episode, we're going to build an AI reader. That is an AI that can analyze human language. This type of task is considered natural language processing, or NLP. NLP is the art of solving engineering problems that need to analyze or generate natural language text. We see it all around us. Google needs to do it to understand exactly what your search query means so they can give you back relevant results. Twitter uses it to extract the top trending topics. Microsoft uses it for in-car speech recognition. NLP is basically extremely dope because it deals with language. Kurzweil once said that language is the key to AI. A computer able to communicate indistinguishably from a human would be true AI. There are 6,500 known languages in the world, and each of them have their own rules for syntax and grammar. Some rules are easy, like I before E except after C, and some are based on intuition since there is no consistent use case. So how do we write code to analyze language? Before the 80s, NLP was mostly just a bunch of hand-coded rules, like if you see the word dance, translate it to danzakudura, or if a word ends in ing, label it as present tense. While this worked, it was really tedious and there are a million corner cases. It's just not a sustainable path to language understanding. The way forward was and is machine learning. So instead of hand-coding the rules, an AI learns the rules by analyzing a large corpus or piece of text. This has proven to be very useful, and applying deep learning to NLP is currently the bleeding edge. So when thinking about what tool to demo in this video, I was really torn between an NLP API called API.AI and Google's newly released English parser, Parsey McParseface. Wow. API.AI takes in an input query and returns an analysis of the text. Parsey is Google's newly released English parser. Both have similar functionality, but I'm gonna go with Parsey because A, it's currently the most accurate parser in the world. B, if you built it into your app, that's one less networking call you have to make, which means you can parse text offline. And C, building this parsing logic from the source allows you to have more granular control over the details of how you want text to be analyzed. Parsey was built using SyntaxNet, an NLP neural net framework for Google's TensorFlow machine learning library. So we could use SyntaxNet to build our own parser, or we could use a pre-trained parser, Parsey. Yeah, let's do that. Once you've parsed your text, there are a whole host of things you can do with it. Let's try it out with our own example. We're gonna build a simple Python app that uses Parsey McParseface to analyze a command by a user and then repeat it back to them, but worded differently. We'll begin by importing our dependencies. Then we'll set up our program to receive and store the user input. The input text is the corpus we'll be analyzing. We can get an array of all the part of speech tags in the input text using the tagger function. So what is part of speech tagging? It's assigning grammatical labels to each word in a given corpus. You know all those words we learned back in elementary school? So take the phrase, I saw her face and now I'm a believer. If we tagged each word in that phrase individually, without looking at the sentence as a whole, we might tag saw as a certain verb, which means this would be a quote from Leatherface. But if we look at this word in the context of the sentence, we realize that it's a different verb. Google trained Parsey by interpreting sentences from left to right. For each word in the sentence and the words around it, they extracted a set of features like the prefix and suffix, put them into data blocks, concatenated them all together, and fed them to a feed-forward neural net with lots of hidden layers, which would then predict the probability distribution over a set of possible POS tags. And going in order from left to right was useful since they could use a previous word's tag as a feature in the next word. So what is a parse tree? Well, part of speech tagging isn't enough. There's another part. The meaning behind some piece of text isn't just the type of word that's being used, but also how that word relates to the rest of the sentence. Take the example phrase, he fed her cat food. There are three possibilities of what this phrase could mean. Number one, he fed a woman's cat some food. That's the obvious one to us intuitive humans, but there's also number two, he fed a woman some food that was intended for a cat. Or number three, he somehow encouraged some cat food to eat something. The meaning of the sentence depends on the context of each word. The team used something called the head modifier construction to sort word dependencies. This generated directed arcs between words like fed and cat being a direct object of the word fed. The sentence starts out unprocessed with an initial stack of words. The unprocessed segment is called the buffer. As the parser encounters words as it moves from left to right, it pushes words onto the stack. Then it can do one of two things. It can either pop two words off the stack, attach the second to the first, which would create a dependency arc pointing to the left, and push the first word back on the stack. Or create an arc pointing to the right and push the second word back on the stack. This will keep repeating until the entire sentence is processed. The system decides which way to point the arc depending on the context, i.e. previous POS tagging. Once that's done, it uses the sequence of decisions to learn a classifier that will predict dependencies in a novel corpus. It applies the softmax function to each of the decisions, which normalizes or adjusts them to a common scale, and does this globally by summing up all the softmax scores in log space. So the neural net is able to give probabilities for each possible decision, and a heuristic called beam search helps decide on the best one when predicting them. Once we have our parse tree and parts of speech variables, let's store the root word and the dependent object into their own variable. variable. We'll call a synonym API to retrieve a synonym for the dependent object. Then construct a novel sentence that repeats the command the users entered back to them in different wording. Looks like it works pretty well. The scope of what you can do with this is so vast. You can use this text analysis to create a text summarizer, or recognize the intent of a query, or understand if a review is positive or negative, or my personal favorite, create a political debate fact checker. Links with more info below. Please subscribe for more ML videos. For now, I've got to go fix a buffer overflow, so thanks for watching.